Alrighty, this is example 2.3. We're still determining internal loads. Here we want to do it internal loads at point C. They tell us we have a journal bearing at A and B. So both of these are journal bearings and they only exert X and C components on the shaft. They even tell us the reactions. So if we want to figure out what's going on at point C, we're going to section. When we section, we can pick either like this more left or right hand or forward or back section. Regardless of each of the halves that we pick, we have a bearing at either end. So it's going to be to our advantage to first get the free body diagram of the whole thing so we can solve for the reaction forces at A and B. And then once we know those forces at A and B, we would cut it or section and then pick either one. Alrighty, so they tell us, hey, they're journal bearings, right? So they're not gonna they're not gonna prevent any translation of the shaft about the y-axis. It's a very bad design, but it simplifies this problem. So we'll go with what they gave us. So they're telling us, hey, there's only a reaction force in the X and Z, which means both A and B are not gonna allow the shaft to kind of slide along the X or along the Z, which is kind of up and down. So I'm going to go ahead and assume some directions here for AX. So I'm going to assume positive AX and I'm going to assume positive AY, assume positive BX and positive, this is BC and I say AY over here. My mistake. I'm thinking up and down, that's Y, but this is Z in this coordinate system. Okay, and they're positive because they're pointing towards the positive X and the positive Z direction. At least that's what I'm assuming. Now let's see if that's a correct assumption. So now let's solve for reaction forces in 3D. Alrighty, so how do we do that? Well, we can try summing forces. If I sum forces about the X, I'm gonna have AX and BX, right? Two unknowns, one equation, not a good one. If I sum forces in the in the Z direction, two unknowns, not a good approach. So it's gonna be to our advantage to start instead with summing moments, right? So we're gonna sum moments. The first question is at which point? Well, the point that has the most number of unknowns. Here, A and B both have two unknowns, so either A or B is a good point to start with. So let's go ahead and start summing moments at point A. Specifically about which axis? So let's do about the z-axis first, or let's go alphabetically. The sum of moments. Let's do the sum of the moments about point A. And this is about, at point A, about the x-axis. So we're looking for stuff that's going to make it swing kind of like that. All right, we're going to set those equal to 0. And what do we have? Neither AX or AZ participate. They're passing through point A. So the next question I need to ask myself is a 300 Newton force here pointing down would create a moment in the X direction. And the answer is yes. If I'm pinned over here, the sky force is down. So it's going to make it rotate like that downwards. So what do I have? I can treat these two individually, or because the distance of the two is the same, I can just get the resultant of the two and add it. Maybe that's confusing for you. I don't know if you've seen that before. So let's just go ahead and separate, right? So I have 300 newtons, that's the force. The distance between the force and point A is 400. So 3 times 400. If I'm pinned at a Z, what is this going to do? Well, if I'm pushing down, it's going to make it swing kind of like in that rotation. If I use the right hand, it's going to be in this direction. Notice my thumb pointing towards the negative x-axis, so that would be a negative moment, right? If that's from one side, and I have another force at the same location, so another one, minus 300 times 400. Again, we could have added the 2, just get the resultant of the 2, which is the same thing as we're doing here if we treat them separately. Well, what do we have next? We have applied force in the X direction. So forces in the X will never cause a rotation about the X. They want to translate. So these are not going to participate, which means BX is not going to participate, right? It's also in the X. So the one that will participate is our BZ force. If we look at BC over here, it's trying to pick up the shaft from this end. So it's going to make it rotate like so. That would be, with the right hand, oops, sorry, I don't know if you can see this, but it would be a rotation like in that direction, which is towards the positive x, which means that would be a positive moment. So plus bz, excuse me, and then times the distance. So the distance between A and B is 1,000. I checked that before. And this is it. So we have one equation, one unknown. We can solve for BC from here, right? So BC is going to be what? Well, I'm going to move these two to the other side. They're going to become positive and then divide by 1,000. So I have 300 times 400 plus 300 times 400 divided by 1,000, and I have 240. It's a positive number, so it means that the direction that we assume for BC is the correct one, 240 newtons. Alrighty, so we have the first one. What else? Well, we need to figure out for BX. How can we do that? Well, let's see. We have sum of moments at point A about x-axis. What would happen if we do sum of moments at point A about the y-axis? So in this case, we would be checking for rotation of the shaft. Because the z component passes through the y-axis, we're not going to be able to solve for BZ. Actually, we already did. I'm sorry. But BX also passes through the y-axis, so we're not going to be able to solve for that one. So some of the moments at point A about the y-axis equals 0. It's no good equation. So next, we'll try the sum of the moments at point A about the z-axis. So now we're looking for stuff that's going to rotate in this direction. So let's go ahead and start. So we're starting at point A. I'm going to start here and I'm going to sweep away from point A. Right? AX, AC are at point A. They're not going to generate a moment at point A. 300 Newton forces, they're in the negative z direction. A force in the z does not cause a rotation about the z. So those two are not going to show up. Instead, what we're going to have is this 500 Newton forces, right? They're pointing towards the positive x. So I hope you can see that this guy are going to make it swing like so. So over here, I'm just going to take the resultant of the two. So 500 plus 500 is 1,000. Is the equivalent. That's the resultant of the two. And they're going to be a distance of 400 plus 350 or 750. This is millimeters. Sorry, millimeters. Anyways, the unit doesn't matter. So I got force, I got distance. The next question is, what is the direction of the moment generated by these two forces, right? Well, they're going to make since they're pushing this way, they're going to make the shaft rotate like so. If we use the right-hand rule, that rotation is in this direction, right? So imagine here, I hope my arm is not in the way, but it's doing something like this, right? So notice my thumb is pointing down, so that would be a negative moment. Next, I have reaction forces BX and BZ. BZ is in the direction of the axis, not going to participate, but BX will. So the force is BX. The distance is going to be 1,000 millimeters. And this guy is also going to generate a negative moment. So here we go. We can solve for the reaction force BX from here. How would I do so? I can move, for example, this to the other side becomes positive and then divide by a negative 1,000. So 750 times 1,000 divided by 1,000 is just going to be 750, right? So BX is going to be equal to minus 750 newtons, right? We got a negative, which means the direction that I assume is incorrect. And hopefully you can see that although I went on autopilot, like, oh, positive AX, positive BZ, it makes no sense because, well, look at the free body diagram. I already have something trying to slide it here along the x-axis, trying to slide it this way. I'm going to need both BX and AX to push it back to keep it in equilibrium. So this negative number makes perfect sense. So we already have BX and BZ. You might be tempted to, you say, you know what? That's it. I want to save a couple equations and I'm just going to use the kind of this front half or this right hand side to solve for my internals. if these math is right and these numbers are correct, yeah, it would give you the right answer. What I like to do is always check my statics because I don't want to do a bunch of work and then using wrong numbers. It's really gonna hurt me in this class. So what I will do then is try to solve for the reactions AX and AZ. How would I do so? Well, I can solve forces in the X and solve for AX. I can solve forces in the Z and solve for AZ, but that's going to depend on my prior or previously determined value for BX and BZ. Here, a much better approach would be to sum moments at point B. So I cancel these guys out and I figure out a value for AX that does not depend, again, on BX and BZ. And then some forces in the X and the Z to check my answers. So let's do that rather quickly. So let's do sum of the moments at point B now, and this is going to be about the x-axis. Make it equal to 0. So we're at B, and we're looking for stuff that's going to make it swing about the x-axis. So basically, in kind of like in this direction. Anyway, so I'm going to start sweeping away from point B. I got this 500 Newton forces. They're in the x-axis. They're not going to generate a moment. Next, I have the 300 newtons. I got two of those. So if I add them together, 600 newtons, right? And they're going to push down, right? So with the right hand, make sure you're using the right hand here. That would be a rotation here like so. Notice that twisting puts my thumb over here pointing towards the right. So this is a positive moment. The force is 600, right? 300 plus 300 is 600. And then the distance to point B is going to be 350 plus 250, which is 600, I believe. 3 plus 2 is 5 and 50, yes. And then what do we have after this 300 newtons force? Next we have AX and AZ. AX is oriented in the X direction, so it's not going to cause a rotation about the X axis, but AZ will cause a moment, right? The distance between point A and B is 1,000, so AZ times 1,000. And then the question is that moment generated by the force AZ at point B and about the x-axis, is that a positive or negative? Well, if I have this shaft and I pick it up, it's going to make it rotate like so. See, my thumb is pointing towards a negative x-axis, so that would be a negative moment. I got nothing else, so the sum of all of that must be equal to 0. So I can solve for AZ from this equation, right? So I can move AZ to the other side, for example, and I would have 600 times 600, or 36, I'm not going to mess it up. So 600 times 600, and then divided by 1,000. 600 times 600 divided by 1,000. Or 360, I should say, newtons. Notice when I do that, 600 times 600 becomes, oh yeah, look at this one. I made something wrong here. 600 times 600 is positive. When I move it to the other side, becomes negative. And then divided by a negative becomes a positive number. But this doesn't make sense. Hold on, this is AZ. I know, this does make sense, sorry. So that's a positive number. Makes sense, why? Okay, let's go here to our shafts. We have the 300 and 300 forces pushing down. So I'm gonna need both AZ and BZ to push up. So it does make sense. I was confusing it with the force in the X. That's what I was hesitating. Anyway, so at least the direction makes sense. Now let's go ahead and sum moments at point B. We already know that about the y-axis doesn't do us any good. So let's do now about the z-axis and make it equal to 0. So now we're looking for these types of rotations, right, at point B. So what do we have sweeping away? We got 500 and 500, or we can get the resultant of those two, principle of moments. 1,000 times the distance to point B. So from here to point B is 250. And then what is the direction along the Z? Well, if I'm pinned here and I push that way, look at the right hand almost pointing to the right answer, right? It's going to push the whole shaft that direction. My thumb is pointing in the positive z direction, so that's a positive moment. The 300 Newton forces, they're in the z. They're not going to generate a force about the z-axis. A z is not going to generate a moment, but we have ax. So ax is the force. The distance is 1,000 newtons. I'm sorry, 1,000 millimeters. And if we're about the z-axis, right, that ax is going to push like so. And that's going to generate a positive moment as well, supposedly. Those only the only two forces that can generate a moment, the sum of those must be equal to 0. So when we solve for ax over here, notice we're going to get a negative value. I'll move this to the other side and divide by a positive 1,000. I think I can do that one on my head. This should be equal to 250 newtons. And it's negative. So let me put it under parentheses. I put this one as well. Negative. Again, this negative ax makes sense. I already have something trying to push it here in the x. So I'm going to need something from both ends to kind of push it back. So at least the direction makes sense. Now let's see if the numbers make sense. If they're right, so let's sum forces in the x direction and ask, is that equal to 0? So let's start. I'm going to sweep here from front to back. I have ax oriented in the positive, but we got a negative, right? So really this is minus 250 newtons. This is z. And then I have plus 500 and 500, or plus 1,000 from these two. These are the applied loads, so underline on blue, 500 plus 500. And then bx, we assume pointing this way, but we got a negative number, right? So minus 750. We almost don't even have to plug it in the calculator, right? Minus 250 minus 750 plus 1,000 equals 0. So we know, or we have super confidence now in both our bx and our ax. If we do in the z component now, we got a positive value for z. So I'm sorry, az. So AC is 360. Next we have minus 300 minus 300. And then BZ, we said it was positive, so plus 240. That equals 0 as well. So now we're super confident in all our reaction forces. I didn't write that equation of equilibrium, but now we're confident with all of these, which means we can move to the next step, which is actually picking either the, how should I call this one? Maybe the left hand and the right hand, or the one in the back or the one in the front over here. So I always, well, here there's no easy way out. So what I'm gonna do is go ahead and draw the free body diagram of this one over here in the back. Because when I cut the section, I like to see at the exposed section. So let me put you on pause while I draw it so I don't bore you with that, and then we'll continue. All right, so I drew here this section over here. So from A to the pulley is 400 millimeters, and then from that pulley to point C is 150. I over exaggerated the diameter of the shaft just to make it, I guess, clear. Hopefully it doesn't confuse you, but that's what we got. Those are the distances, right? That pulley over here has two 300 Newton forces, one at each side. This could be from like a belt. And then we already determined our AX to be 250, right towards the negative x-axis. So I applied it over here. And AZ, we said, was 360 newtons pointing up. So now what we have to do is we cut it, and we have to figure out the internal load. So when we cut, right, this was not welded, but it was part of another thing. So basically what we have is a fixed connection, which means we can have up to 3 forces and up to 3 moments acting at point C, right? Since I teach statics, I like to think of these as a force in the X, Y, and Z, right? So there would be like a force here along the X, which I would just assume here along the X, a force here along the Y, or positive Y, and then a force along the Z. From solids, we know that these forces Hold on, I have notification on my screen. I'm running out of battery. Sorry. So from solids, we know that these forces have special names. So this one on the Y, which points away from the section, this is going to be the normal. So we'll call it N. You might see it as NC, like the normal at C. Next, we have this one, which is parallel to the cut. So this one is the shear force NC, and this is about the x-axis, VCX or VBX. This is VCZ. Sometimes you'll see it like this. So the shear force at C about the X, the shear force at C about the Z axis, the normal at C. And then we have moments. So here I just assume positive moments, right? So I'll start here with the X. So there could be a moment like so, positive in the X, a moment positive in the Y with the thumb pointing towards the Y. So something like so. And a moment positive in the Z. So something kind of spinning like so, right? So they're going to have special names. This one that is pointing, that is perpendicular to this plane over here. This one is going to be the torque. So this is T. And then these two are capable of producing bending moments. So we're going to call them, for example, this one here, we'll call it moment at point C about C axis. And then this one, moment at point C about X axis. And these two can generate bending moments. This guy is going to generate twisting or a torque. So there we go. We have 6 unknowns, and our job is to determine what are the 6 unknowns. So it's a 3D problem. So 6 equations, 6 unknowns. Let's start with forces, see what we get. So we say sum of the forces in the X direction equal to 0. What do we have in the X? Well, we have, let me start over here. We have the 250 at X, so it's pointing towards the minus X, so minus 250. That's from this one over here. These two are in the Z direction, they don't participate. And then the only other force we have is this shear force. It's right, it's unknown. So let me erase that. So let me put a sheet of paper underneath. Sorry. So this shear force at point C about the X-axis, we assumed it to be pointing towards a positive X, so that's a positive shear force. And we got nothing else. So from here we can solve for the shear force about at C in the direction of the X-axis. I'm going to move this to the other side, so this is going to be equal to 250 newtons. This is in the X. Next, let's do sum of forces in the Y direction. So sum of forces in the Y direction. Y is this way. So in this end, we got nothing in the Y. These are in the Z direction, the 300 newtons ones. So that means that we only have our shear force and, well, we don't have a shear force. We call that one the normal. So it's got to mean that that normal, or that force in the Y, is equal to 0. Again, because there's nothing else in the Y direction. So there's nothing trying to stretch this guy. Let's finish it off. Some of the forces now in the Z direction equal to 0. What do we have? Well, at point A, we have positive 360. And then we have minus 300, minus 300. So minus 300, minus 300. And then we have our shear force in the Z direction, which we assume positive. So plus the shear at C about the Z direction. There's nothing else. So the sum of all of that must be equal to 0. We can figure out what the shear force is. VZ about the Z. By moving everything to the other side. So I got minus 300 and minus 300. That's going to be positive 600. Minus 360, which should equal 240, right? Yes. So it's 240. And that's a positive number. So this is newtons. It's a shear force. There we go. Next, we need to figure out the moments. Is this thing still recording? Yes, we're still recording. Let's figure out the moments. So let's sum moments at, it doesn't matter where we sum the moments. Should we do it at point A, at point C? Doesn't really matter. Let's do at point C here since it's kind of highlighted and it's drawing my attention. So let's do sum of the moments at point C about, let's start with the x-axis. Must be equal to 0. So we're looking for moments in this direction. Positive x is this way, right? So we have here the bending moment at point C about the x-axis, which is this guy here that we assume to be positive. Everything else here is crossing that C, right? So we have most unknowns here. So none of those forces can generate a moment at point C, and all the other moments are in different axes. So we're covered. We move away, now we have 300 and 300. So we add the two together, we get that resultant. We have 600 newtons, and the distance is 150. Right? And if I'm pinned at C and it's about the x-axis, these pushes down, that's going to generate a positive moment. So plus positive moment. And then we continue moving away. We have AX cannot generate a moment about the x-axis, but AZ can, right? So next we have 360. Now the distance between AZ and C, we got 400 plus 150, which is equal to 550. And the next question, is that a positive or negative moment? Well, I'm looking for rotation about point C. The force here points up like that, so it causes that kind of rotation. My thumb would be towards the negative x, right? Because positive is this way. So that's a negative moment. The sum of all of those must be equal to 0. So we can solve for the moment at point C about the x-axis by just moving everything to the other side, right? So we're going to have minus 600 times 150. And then this is going to become positive, plus 360 times 550. And this is giving me a moment of 108,000 Newton millimeter, or that's way too big, right? So let's just move the decimal 3 spaces and just call it 108 Newton meter. So this is for this guy. Next, let's do the sum of the moments at point C, but now about the y-axis, and make that equal to 0. So what do we have about the y-axis? We have this moment, which we call it the torque, right? So we got the torque. Nothing else here in red is going to generate a moment about the y, right? Because the forces pass through the y-axis and the moments are in other axes. Next, we have the 300 Newton forces, one on each side. So these two have an effect. They can generate moments about the y, but because they're equal distant from the y-axis, one wants to rotate the shaft in this direction, right? So like this. This one in the back wants to rotate the opposite way. They're the same force and they're going to be the same distance away from the y-axis. We don't know what it is. They didn't give us the diameter or radius, but they're completely balancing each other out or canceling each other. So they're not going to, at the end of the day, these two cancel each other out. There's no net rotation about the y. And then AX and AZ cross that y-axis right there. So nothing else can generate a moment about the y. So that means our torque has to be equal to 0. And now for the last one, some of the moments at point C now about the z-axis. We're looking for this type of rotation, right? We're going to have our initial unknown over here, this one, MC, the moment at point C about the z-axis. We assumed it to be positive, right? And then we have the 300 Newton force. They're in the z-axis. They cannot generate a moment, and these will never make it rotate like that. AZ cannot generate a moment, but AX can, right? So AX is 250 and it's at a distance of 550. The next question is Is it a positive or negative moment? Well, let's look. If we're pushing that way with the right hand, that would cause a rotation like so. I don't know if you can see it, sorry. It's pushing that way. So the thumb is pointing down, that's in the negative Z. So that's a negative moment. There's nothing else, so the sum of all of that must be equal to 0. So we can solve for that internal moment at point C about the Z axis. We move this to the other side, becomes positive. We have 250 times 550, which is 137,000. We'll move the decimal point, so we'll just call it 137.5 Newton meter. We can run that one to 138. Okay, so we're done. We got all the internal loads at point C. Here is just a tip. If you wanted to, you could have looked at the other half of this shaft over here, like so. And so the cut would be on this same C, right? But it would be the hidden edge. You could still come up and figure out, okay, what is the normal? Then the VC, the shear in X, the shear in the Z direction, and then as well as the torque, maybe like so, and the bending moments over here. If you go and look at the other section over here, because this is a 3D problem, you should be able to get exactly the same